Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hi, and welcome to today's Australian Water School webinar titled From Courant to Saint-Venant. I'm your host, Craig Price, and I'm thrilled to be able to introduce you to our expert presenters and panelists today who will help us dive inside the black box of some of the equations that are in our hydraulic modeling software. So for today, let's give a welcome, first of all, to all of you from around the world, tuning in not just from Australia, from the United States, from all continents around the world. We are thrilled to have you with us today in whatever time zone you happen to be joining us from. Now, for today, have you all say hi to us today. Just starting in the order that I see you on my screen right now, which is with Euler first. Go ahead and tell us where you're coming to us from and a little bit about your background and what you do.
I'm based in Brisbane, Australia. I'm working at the University of Queensland for the past 32 years, and I'm really working on open channel hydraulics and hydraulic structure as my main business.
Excellent. Casey, where are you coming to us from today?
Hey everyone, Casey Kramer coming from Olympia, Washington, up in the Pacific Northwest in the United States. And yeah, my area of focus is mainly in transportation hydraulics. Nice to see everybody.
Excellent. Good to see you. Mike, welcome.
Hi, I'm Mike Konechny with HDR, located here in Sacramento, California. I'm a senior hydrologic engineer doing mainly hydrology and reservoir operations.
Excellent. And Chris, a familiar face to us here on the Australian Water School's channels. How you doing today?
I'm good, Craig. And hello, everybody. I'm coming to you from Portland, Oregon. So now I think we've got all three states on the west side of the U.S. covered. Here, I'm with Kleinschmidt Associates, and I've been in the business of hydraulic engineering, hydraulic modeling for about 27 years.
Excellent. All right, so the way this is going to work, we're actually coming at you from both sides of Australia here as well. I'm on the west coast of Australia, and Hubert's over on the east coast. So we've got a couple of continents here, and then our presenters for this upcoming course series will be joining us from Europe and elsewhere around the world. We're looking forward to that. So thanks to our presenters, we'll bring you back on in a few minutes. We've got this Hydrology and Hydraulics Essentials course starting tomorrow. And what we're going to do is take things back to first principles, all the way up to engineering applications. And this course then begins tomorrow with meteorology and precipitation. So we're going to start with the water cycle, evaporation, get it up into the clouds, and then the raindrops. So we've got infiltration and losses, where how much of that rainfall turns into runoff in course number 2. And then we route the flow, route the hydrographs in course number 3, talk about the lag times, how much of the rainfall turns into runoff, how we deal with base flow, and what we do with these hydrographs along the way. We'll then take this into statistical or probabilistic and stochastic hydrology and look at the probabilities of certain rainfall events occurring. From there, we'll bring it into hydrostatics, which we'll learn a bit about why a diver at the bottom of a small tube like this senses nothing differently than a diver at the bottom of the ocean, and why, as you can see in this MythBusters special, why a diver who loses the compression and the compressed air inside of the suit here, why it's the same at 100-meter depth as getting run over by a steamroller. Those are the kind of concepts that we'll be covering here. We will then move into 1D, 2D, and 3D flow, taking it from the static hydrostatics into hydrodynamics, moving that flow around and seeing what happens to the bridge piers and what kind of forces act on those, what kind of erosion we'll get as well. Go back up to this one here, and we'll look at 1D, 2D, and 3D modeling applications, pipe flow, hydraulic structures, turn it into flood hazard and classifications and flood mapping. So that's those are the concepts that we're going to cover. And again, we're going to start with Newton's laws and the basic physics, and we're going to then see how that transforms into the water world and how kinetic and potential energy are much the same, whether you're looking at pendulums or bowling balls or whatever else it is that's moving with a given potential energy as it's converted into kinetic energy and back again. Could you ever get back up to this point? No. Why not? Because of the friction losses, the head losses, the inlet losses, and things like that. So we will, again, take it back to first principles, which we started with in our first introductory webinar for this course series 2 months ago, which was called Fruit Dude. Now, during that presentation, we were joined by April Choi, who is a engineer, a NASA scientist who looks at all sorts of things and is also a world record holding whip cracker. I'll play you something on one of her appearances here on the Smarter Everyday channel, where she mentioned something that kind of sparked her appearance on our webinar 2 months ago.
It depends whether or not you're using a Lagrangian framework, which centers on here, or a Eulerian framework that centers on the overall mesh.
That's what I was thinking.
And so she mentions here a Eulerian versus a Lagrangian framework. And I wanted to ask you the question here, the way that's pronounced there, when we use this man's name, Leonhard is his first name, his surname here, what does it rhyme with? So I'm going to ask you all this question, and you can answer me this. Does it rhyme with Bueller, or does it rhyme with boiler? And you may have heard, as we answer this question, I'll give you just a minute to answer this. In the background, this is not a hint. This is just a background sound. Don't let this influence your vote. And then what we'll do is have a look at what those results might be, along with some of the other panel results that we might have had. Joel, if you can pop up those panel results whenever those are ready, we'll have a look at that and see what the votes were. Wow. Okay. So we have Bueller in at 50% and 52% and boiler in at 48%. So Leonhard Euler is Swiss, and that's how you would pronounce it in Swiss. So it's actually Euler. And so we'll hear a little bit about Euler here and get the correct pronunciation that they have in this this movie clip here. If you've seen this movie, Hidden Figures, you'll hear the answer.
Euler's method. Yes. That's ancient.
So they say Euler's method, Euler's method, Euler's method. So before we get into the Courant and Saint-Venant equations, I wanted to introduce this concept of Euler's equation, and the Eulerian, or people say the Eulerian versus Lagrangian frameworks. And so what she shows us here is in this movie clip that's based on Katherine Johnson, a real-life character who did help NASA get the Apollo mission going and figure out the trajectories here. What does this all have to do with water? And when you have a look here then at this slide, that just shows the clip of the equation that she's looking at here. And here's these water circulation patterns. This is a model I built just for fun of Hobbiton in New Zealand. This is flooding out the hobbits. And you can see some of these circulation patterns here. Well, think about the Earth and the Moon and what we're doing with these trajectories. As we move a spacecraft, in this case, around these trajectories, they needed to compute all the forces at any given time on it, the gravitational forces, the inertial forces, where is it moving, and how do you define the positions with X, Y, and Z, basically, 3 coordinate positions. And when we do that, and we're moving this around, if we take an X and a Y axis, and we move this spacecraft up to a given point that we've got here along this trajectory, if we can try to compute these forces here and move along this path, in a given delta t, the dt, you will have a given error. So if I take this trajectory and take its slope and its velocity and move it consistently or constantly along that trajectory path, I can estimate where it is in this position, but the longer my time step is, the farther off I'll be by the time I do the next computation. So we want to get this dt as small as possible. Just like a circle can be approximated by a whole bunch of little segments, at which point it will still look like a circle, that dt is important. You don't see me right now as an animation. I mean, you might think I'm moving, or that I'm moving my hand, or that I'm moving my mouth, but what you're seeing is a series of static images, individual little time steps. The better the frame rate, the more accurate it's going to look. And that holds for movies as well as the Apollo mission, as well as for our hydraulics. So what did Euler do? How did he contribute to what we do in fluid mechanics or even in hydrology? your homework, and this is a bit of a preview to the course coming up here, your homework is to make see if you can make a Eulerian path around your city. Now, in the city of Königsberg, which was studied by Euler and walked by Euler in some cases, he noted that the 7 bridges that you have here, if you had a rule that said you can only cross every bridge once and only once, could you do it? And I think even in somebody in year 3 or year 5 or what in an exam question would realize very quickly that it can't be done. But can you prove that mathematically that it can't be done? And that's what Euler did. And so by representing things like this, these little connections as a series of nodes and paths, you basically take this entire waterfront up on this area and turn it into a single node, because it's all the same to the computer in this case and to the equations. And so by connecting that, I would be curious then, Chris and I, I've spent a long time in Portland where Chris is from. Could you cross all of the interstate bridges once and only once? And so in your city, that's your homework. Could you do the same? Can you take the bridges? If you don't have rivers in your city, take the highway bridges. Can you cross them all once and only once? And if so, then you can make a Eulerian trail, which some cities actually have in commemoration of Euler's contributions to mathematics. Now, one of our presenters in the course tomorrow is joining us from the Amsterdam area, from the Netherlands. Here's a look at the bridges in Amsterdam. Imagine what it would take in terms of computing power to work out even this simple schematic. And so these kinds of schematics, that's how we take and represent our catchments, our watersheds. Now, let's talk about Courant. Courant now is if you're ever going to publish a paper, it's a benefit to have your name first in the alphabet. I don't know if we should have called this the CFL law. 3 Jewish members of society that fled the Nazis back in the 1930s developed this relationship that we now essentially refer to as the Courant number. And so when you take these, you take a surface and we try to discretize it or rasterize it in a number of different ways. We can take different sorts of meshes and represent surfaces that way. The grid size becomes very important. So if I take, for example, a 50-meter grid, this is 50 by 50 meters. This is one little grid cell inside of one of my hydraulic models. And this one, when I ran the entire model, ran in about 10 seconds at a 50-meter grid size. So that was awesome. And it had maybe a few thousand grids. When I move here to a 20-meter grid, it took 3 minutes. A 10-meter, 5-meter, 2-meter. Now I'm at 2 days. And when I get down to a 1-meter grid, this one took 14 days to run for the entire model, which was millions and millions of grid cells. So we did that for a benchmarking study at one point a couple of years ago. And so is there an advantage in getting down to this level of detail? Well, when we're looking at the Courant number, we often deal with optimization. So the Courant number, if I were to take, assign a definition to it in my own words, it's basically the number of grid cells per time step. And so if I were to take my area here, this is a floodplain area with some sheet flow, it becomes a little more difficult to determine flow directions and things like that when you've got very shallow flow. But if I take this and divide it up into a number of grids and try to transfer flow, like the raindrops that come down here, and move into from one cell to the other, there's a Courant number of 1. That's one time step, it moved one cell. Here's a Courant number of 2. And then if I take a Courant number of 3, it moves out to this third cell here. Oops. And so the Courant number can get the derivations of the Courant number can get very complex. Here's a NASA paper that involves the Courant number, and you look at all this, and obviously you can't read the text that small, but it gets very overwhelming very quickly. And some of the equations we'll talk about today, including the Navier-Stokes equations in some forms, this is the spherical form of it, can look a bit intimidating. And when you see the Greek letters, it's sometimes people who have been out of school for a long time like me can feel a little bit overwhelmed. Well, you can be stoked about the fact here that the Courant number equation is quite simple. And so what we get this one narrowed down to is the Courant number is equal to the velocity, including in this case the addition of the wave celerity. The root GD is what we covered last time in our presentation on Froude. and the Froude number, and how we determine critical and supercritical and subcritical flow. The root, sometimes it's called the root of GH. So that wave celerity gets added on, and then the only Greek letters we need to deal with in this equation are delta. That's the only one we need, and all that means is the change in time. And we essentially approximate this as the velocity times the change in time, which is our time step, and that's divided by the change in distance. Now, before I get into moving this equation around, I just wanted to bring Chris back on here. Chris has done a lot of lecturing on the Courant number for some software training courses and things like that. And I wanted to go back to this question here where we have the velocity and then we have the wave celerity. And a lot of times hydraulic models will look at the water that's moving and ignore the wave celerity. And I guess one question would be, is that okay? This is what's the equation that's in the Australian Rainfall and Runoff manual right here. And then this is the equation as it sits in a HEC-RAS manual. So that V, should that or should that not account for the wave celerity based on the depth?
Yeah, good question. And in principle, the answer is yes, because that's the equation and that's the relationship that you have between delta T and delta X. But in practice, a lot of times, especially when we're setting up our model, we want to do things quickly. We want to test things out quickly. And getting that root GD can take a little bit of time and a little bit of guesswork, and it can change all over your modeling domain. So a lot of times what we'll do is we'll just pick out a representative peak velocity from maybe a first run of our output and use that instead. But I always think it's a good idea to go back at the very end of your model development phase and consider the square root of GD towards the end and make sure that you're still good with your Courant numbers. Now, a lot of it also depends on whether you're running an implicit or explicit model. With an implicit model, you don't have to adhere to the Courant number as strictly as you do with an explicit model. And so a lot of times you can get away with simply using velocity, and that's going to get you close enough. A lot of people use an approximation for root GD, and I've seen 1.5 times your velocity and use that instead. And that's just a quick way to account for a little wave celerity to get a more accurate representation of your Courant number. Other things to consider too is what's happening in the system that you're modeling. If it's a stagnant lake, let's say, for example, and you have no velocity, well, then everything is wave celerity, right? And so of course you're going to want to include that. So those are just things to think about. But in practice, a lot of times we'll omit the square root of GD just to keep things moving quickly and make for easy math as well.
Thanks. All right, if you can stay on as well, I think I'll ask you for a couple comments again at the end of this here. This boils down to basically, if I come back to this equation right here and we set C equal to 1, the Courant number equal to 1, that means 1 grid cell per computation. This boils down to what my physics teacher in high school called DIRT, and that's distance equals rate times time. So again, we are taking this course starting tomorrow all the way back to basic principles. So if this is one of the very first equations you would have ever learned, distance equals rate times time. If you're traveling 85.8 Ks per hour and you go for 1 hour, that's your time, then obviously your distance is the product of the two, and you have traveled 85.8 kilometers. So distance equals rate times time. Now all we need to do is substitute out then for our equation here, x, which is our grid size for D, and then v for our time step, and for our velocity, and then we multiply that by the time step, and what we'll get then is this equation in very simplified forms: x equals vt, dirt basically. If I want to solve that for t, x over v. So that's easy enough there. If I now take the t over here, I can switch the t and the v to solve for v, and so my v becomes x over t. So I basically have this equation now in 3 forms. And this is as simple as it gets. We have any 2 of these 3 variables that you know, you can find the third. The problem is sometimes when you're starting a model, you don't know 2 of the 3. You might only know 1 because you essentially start with a grid size that you want to use to represent your channel at whatever scale you've got. That's generally the first one that you would know in terms of what you want to start with. As far as the time step and the velocity, well, what would you do with those? So if you're setting up a model, you don't know what the velocity is yet. You haven't run the model yet. And so if you have to estimate your time step before you even run the model, how do you do that? You've got two unknowns. I've pulled up a excerpt here from the TwoFlow wiki, and you can see some of the familiar equations here for the Courant number. You can actually see the wave celerity there as well. Some of the things we were just talking about. Somewhere on this page, you'll see the estimated velocity. And that's the question to you, the attendees, like we're going to do in this course. We're going to have lots of questions back and forth and some interaction. Where in these words do you see the assumed velocities? And the answer in this case is when we have a fixed time step that we're choosing here with the classic model. This is not the adaptive one, but where you would be picking it yourself. The answer is in the denominator, because if the time step in seconds is half the grid size in meters, we are making an assumption there that this 2, the denominator in that fraction, that is an assumed velocity of 2 meters per second if the Courant number is 1, is assumed to be 1. Likewise, if you go to 1/5, you're going to have the denominator being a 5, which means you've assumed a 5 meter a second velocity if you're assuming that the Courant number is 1. So in some cases, as we mentioned, and as Chris mentioned, with the celerity, the wave speed, in some cases, that's not just the object as we have like with the water moving and then its wave moving in advance of that water or in addition to that water to get the actual speed. You might have a material in here, like for these analyses right here, it's actually the stress wave. That's the speed, the wave celerity that gets included. And so you can have beer cans or baseball bats or whatever you'd like. This is all just modeling, whether you've got 1D, 2D, or 3D models, whether it's water or another material. Everybody's got to deal with Courant numbers and with time steps, because again, you're always trying to optimize your computing speed and you're always trying to get as close as you can to reality, realizing that it's just made up of a bunch of fixed points, static points. So that brings us to our next piece here. Again, we've talked a little bit here about Courant. In our course, we're going to bring up a whole bunch of other equations and try to get to the bottom of those. We'll talk today a little bit about Saint-Venant and simplify that down to a diffusive wave scenario. In the course, we'll actually start with Navier-Stokes and see how we can derive Saint-Venant's equations out of that. So if these are things that may sound a little bit intimidating if you've been out of school for a while, or maybe you've never had these and just need an intro to them, whether it's a refresher or an intro, we hope that these concepts that we'll cover, permeability and pressure and head loss and friction, turbulence, viscosity and shear, these are the things that we want to know a little bit more sometimes about the first principles on, and that will help us all be better modelers or whatever it is you do in your water related career. We hope this will serve as a good background for you. So with that, we'll wrap up our part here about the Courant number. We'll get some comments from Chris a little later on to follow up on a couple of those things about the Courant number. And but for now, let's turn it over to Hubert. Dr. Johnson, over to you for a discussion about the Saint-Venant equations.
Thank you very much, Craig. So let us talk about the Saint-Venant equation and their simplification. But as I say, let's start right from the beginning. What are the Saint-Venant equations? The Saint-Venant equations are a system of two equations to solve one-dimensional and steady open channel flow. One equation is a continuity equation or conservation of mass. The other equation is a dynamic equation or conservation of momentum. These equations have been long-lasting. They were first published in 1871 by a Frenchman, Adhémar Barré de Saint-Venant. And in fact, in 1871, Barré de Saint-Venant published two papers. The second paper, which was an application of this equation, was dealing with the prediction of the onset of the tidal bore of the Seine River on its development upstream. And at the time, during the 19th century, the tidal bore of the Seine River was a mighty bore, causing massive impact in relation to navigation, for example. Importantly, the Saint-Venant equations were developed based upon 6 basic assumptions, assuming one-dimensional flow, and in particular, this means that the transverse free surface profile is horizontal, assuming very small streamline curvature. This is a very important approximation that should not be ignored. And in particular, it implies that the Saint-Venant equation assume implicitly hydrostatic pressure distribution. Third, we assume that the flow resistance and turbulent losses are the same in steady uniform equilibrium flow, normal flow condition, for the same depth and velocity, regardless of the trend. Fourth, we assume that we have a relatively small bed slope, that is cosine theta equal 1 and sine theta equal tangent theta. This approximation or assumption is valid within 1% as long as the bed slope is less than about 8 degrees. Fifth, we assume constant water density. So implicitly, we neglect self-aeration and sediment suspension. The sixth assumption is that we are dealing with a fixed boundary channel. This sixth assumption might be released if we introduce an equation of conservation of mass for the channel bed and relevant equation for erosion and deposition. In a differential form, the 7 equations are shown in front of you, with the top one being continuity equation or conservation of mass, the bottom one being the dynamic equation or conservation of momentum. These are typically the equation used in any flood modeling software. If we look more specifically at the dynamic equation, the bottom equation, the first term is linked with acceleration, the second term with inertia, and the last two terms are respectively linked to the friction slope of flow resistance and to the bed slope. Let us look now at the order of magnitude of the various terms on the dynamic equation, and we will focus today on the dynamic equation. If we consider a flood flow with a rising hydrograph, when the flood velocity increased from 1 to 2 meters per second in 3 hours, that's quite a fast rising hydrograph. It's almost a flash flood. The dimensionless acceleration term is of the order of 10 to the minus 5 to 10 to the minus 6. If we have, along a 10-kilometer reach, an increase in velocity from 1 to 1.5 meters per second, for example, because there's a constriction of the channel, the dimensionless inertial term is of the order of 10 to the minus 6. Let us look now at the friction slope and bed slope. And sometime we also looked at the slope of the free surface elevation, defined on the top right sketch. In the lower valley of a number of rivers, field measurements have shown value of about 10 to the minus 2 to 10 to the minus 3. For example, the Rhône River was between Valence and Avignon, at the downstream end of the Rhône River in France. The Brisbane River was in the lower Brisbane Valley, between Moghill and the city center, the CBD of Brisbane. During a flood of the Missouri River, a sudden increase of discharge by nearly a factor 4, from 700 to nearly 3,000 cubic meters per second, was documented, on the dimensionless acceleration term was less than 5% of the friction slope. During a series of floods in Japan, in the Kitakami River, the combined dimensionless acceleration and dimensionless inertial terms were less than 1.5% of the variation with distance of the water depth. And similar results were obtained during the 2011 flood of the Condaman River in Queensland and the Brisbane River in the lower Brisbane Valley. So that brings us to the potential simplification of the 7 equations. Under appropriate conditions, and these are most important keywords, under appropriate conditions, the dynamic equation might be simplified. This simplification applies only to the dynamic equation, and we will always keep unchanged the continuity equation because conservation of mass is uppermost important. One simplification is called the diffusive wave equation. That is, we neglect inertial and acceleration terms. And we obtain an equation here, which in fact is called diffusive wave, because if we transform this equation, the dynamic equation, and express this in terms of the total discharge, BQ, we obtain an equation shown here, which is equivalent to an advective diffusion equation with analytical solution shown on the right, on one, very well-known example of the diffusive wave solution is the H&H method. A further approximation is a kinematic wave equation, whereby the dynamic equation is simplified as the friction slope equals the bed slope. This equation is exactly the same equation as the momentum equation applied to uniform equilibrium flow in a steady situation, basically normal flow conditions. But the kinematic wave assumption is an unsteady system of equation because there is an unsteady term in the continuity equation. Importantly, the kinematic wave can only describe the downstream propagation of a disturbance. Because of its simplification, on the other hand, the kinematic wave equation can be solved analytically, sometimes providing us with validation solution. An example is a monoclinal wave. Another example is a dam break wave down a steep slopes solution of Dr. Bruce Hunt from the University of Canterbury in New Zealand. So let's try to wrap up this short talk. The 7 equations are a system of 2 equations developed to solve one-dimensional and steady open channel flow. The equations were developed with 6 basic assumptions. In the dynamic equation, that is the conservation of momentum, the friction slope, bed slope, and slope of the free surface elevation are always important, with value here in the lower region of a number of large rivers. Under appropriate conditions, and only under appropriate conditions, the dynamic equation may be simplified. Also, we will always retain the continuity equation unchanged. And we have briefly discussed 2 simplifications, the diffusive wave and the kinematic wave. For those interested, here are some relevant literature, and I use this opportunity to bring to your attention the forthcoming Hydrology and Water Resource Symposium in Brisbane at the end of November, with the call for abstract being open on until the 20th of May. Thank you very much, and back to you, Craig.
Excellent. Thank you, Hubert. If anybody has questions about that presentation, please keep those coming in the Q&A line. We'd invite all of our panelists now to come back on and join our panel discussion here. And as needed, we may share some screens and get back to some slides that might illustrate some of the points that you might want to address. What I'll probably start with, maybe I'll go to back to Chris first of all, just for any follow-up on the Courant number that you wanted to offer, and then there is a question here that was addressed directly to you that I think you might have answered already in terms of implicit and explicit. So first, just any follow-up items on the Courant number discussion, and then implicit versus explicit.
Yeah, and I don't know why it looks like my video is not working. I don't know if you can see me.
Yeah, we see you just fine. Yep.
Oh, you do? Okay, I don't see me, so I'll trust you. Yeah, one more thing I wanted to add on the Courant number discussion is, the importance of keeping things practical, especially at the beginning when you're building and testing your model. And because I'm a little bit lazy, I like to keep things easy mathematically. And so that I kind of hinted to that as to why I don't consider the square root of GD, at least early on. But I also like to, when I'm approximating what I think velocities may be, I like to use nice round numbers, or numbers that are nice divisors of my cell size. For example, if I have 100 meter cells, I like to think of in terms of 2 meters per second or 5 meters per second. Makes for easy math to figure out your delta T. So just something to keep in mind. Now, there was a question directed specifically around the difference between implicit and explicit solution schemes. And I don't know how deep we want to get into this yet, but I'll give you my quick bird's eye view perspective on the difference there, and then maybe look to some of the other panelists and maybe Hubert especially for a more theoretical look at it. But the way I consider implicit versus explicit solutions is an explicit solution is a stepwise solution spatially in a modeling domain. And so if you're trying to solve, say, water surface elevations, you'll start at one point and you'll run your computations in a spatial direction to get the next point, and then the next point, and the next point. An implicit solution considers all modeling or all computational nodes in a modeling domain together, and you actually solve that simultaneously using an inversion of a matrix. And the result, or the practical result of an implicit solution, is you can usually get away with a larger time step because it's a more stable consideration of the solution. So I don't know. Does anybody else have any additions to that they want to throw out?
Yeah, Hubert, go ahead.
Look, Chris, you get the right point. I think perfect explanation. I'm going to share here the way my students sometimes think about explicit versus implicit. Explicit is very easy to code, but an explicit calculation will diverge very rapidly. After typically a few hours, 6 hours, 12 hours, 24 hours, it will diverge. So every time we do some numerical modeling of more than 24 hours, I will say, typically you should go to an implicit scheme.
Yeah, thanks. And I think, Casey, if you had, there was a couple of comments that you had there, you might want to follow up on that question as well. But then I saw this question about adaptive versus fixed time steps. And because a lot of the modeling that you do goes from a very large scale for a watershed or catchment, getting the water into the river, but then you're looking at a very small scale when you're looking at individual bridge piers, because you do a lot of design for scour calculations and things like that, where you have to look locally right at that bridge pier. And the time steps can vary vastly, from what you would need in a natural system or in a larger river versus when you're looking immediately at the structure itself. So, any comments on adaptive versus fixed time steps?
Yeah, I mean, it really depends on selecting that most appropriate model for the task in hand. But to your example, for utilizing bridge scour, and where Courant condition would matter, going back to Chris's point and your equation you were showing, is that you would want to be looking at that cell size that you would need to get the correct hydraulic characteristics around that bridge pier, and getting an estimate velocity and then an estimate of your smallest cell size to get that largest ratio, and then setting that accordingly. Yeah, so yeah, unfortunately, when you do need those detailed characteristics, that's usually what's going to drive your time step, and thus probably take a longer model runtime.
Yeah, thanks. I wanted to let's hear from Mike as well. I saw a couple of questions here about conservation of mass and things like that. And I know your specialty and the way you're helping out with these courses coming up is more on the hydrological side of things. But when you think about a stream or a reservoir or a storage unit within a hydrological model, where what inflow minus outflow is got to equal the storage. Any comments on conservation of mass, and then moving that into conservation of momentum versus conservation of energy? There's just a couple questions there that you might have seen on the Q&A line that deal with that.
Yeah, that's a great point, Cray. So, I mean, in general, we shouldn't violate physics. And so conservation of mass and conservation of momentum are pretty fundamental. And I think those are easily measurable and observable. And so getting those right is very important. So when there's certain assumptions that happen at the smaller scales of time or space, maybe we can kind of wave our hands to some degree and get a close enough approximation where don't let perfect or be the enemy of good enough. And I think but making sure that the mass or the volume is right is key in all hydraulics and hydrology.
Yeah, and as Hubert mentioned in the chat line, you must fulfill conservation of mass, otherwise it's wrong. But every model is going to have a residual mass balance error. The question is it significant? And so it might be 0.000 something percent, or once it gets up to 1 or 2%, that doesn't sound like a lot, but that can really affect your localized hydraulics. I've had a couple of other questions that I saw come in about the assumptions of inertial and acceleration, and in the diffusion wave. Hubert, that question I saw that you had answered already about the flash flood. Maybe if you could just restate that question, because those watching the YouTube recording won't have that to see.
So the question was really related to the relevance or importance of the acceleration of inertial terms in the dynamic equation, which led typically to their, let's say, assuming they are negligible, to go to the diffusive wave equation. Strictly speaking, the acceleration of inertial term will only be important when you have a fast rising hydrograph, typically a flash flood. When you have a mega flood with a slow rising hydrograph, you can nearly always ignore these terms, because they will be typically 1,000 to 10,000 times smaller than the friction slope on bed slope terms.
No, thanks. Yeah, that's a good point. And some of the acceleration, like that you were talking about, you know, when you think about a vehicle, an automobile going from 0 to 100 k's an hour in a certain number of seconds, you know, that's an acceleration. It's also an acceleration when the car slams into a wall. That it's just negative acceleration. It's deceleration. Anytime your velocity changes, and that's a vector, it can be either the magnitude or the direction or both that are changing, then you have acceleration. And so looking at your system and recognizing when you've got these terms that need to be accounted for versus when they can be ignored is going to be very important. And one of the things we'll do in the course, we didn't get into it in this webinar, but we'll start with the equations that account for everything from Coriolis effects to the differences in Earth's gravitational pull all over the place, all the things that you can kind of approximate and start eliminating from your equations to simplify them. You know, there are certain things that only become important when you know, in certain systems. You know, maybe it's a scale of a system, or maybe it's a speed of a system. Chris, I wanted to ask the question then about, you know, back to this adaptive versus fixed time step. The advantages, like, for example, in a dam breach model, that's something we've covered in some of our dam breach courses, and I think it might be relevant here to mention how changing your time step during the simulation can be very advantageous in terms of computing time when you've got something as dynamic as a dam break.
Yeah, going back to your simple equation for Courant number, you know, it's a function of your time step is a function of your computational node spacing as well as velocity. Well, velocity can change in a model simulation. If we're talking about something like a dam breach or a flash flood, you may have a period of your modeling simulation where not much is going on. You've got base flow conditions, velocities are very low. That's going to allow you to use a larger time step and still meet your Courant number condition. But then when you have the breach flood wave coming through, velocities pick up, and sometimes to an extreme degree, in which case you would need a much smaller time step. So having the ability to adapt your time step to the changing velocities in your model is very critical in maintaining very efficient models, which is something we always want to do. We do want to have accurate models. We want to adhere to the Courant number, but we also want our models to run as quickly as possible, because nobody wants to sit around and wait for hours and hours or days for your model to run. So having that ability is very important.
Okay, thanks. If you could follow up also on the questions that you've been answering here about the Courant number. I guess I want to back up a bit to what I said about all those equations I was presenting, where we assumed the Courant number was 1, and you know, these attempts to try to get it less than 1 if you're solving it explicitly. Implicit, like the word implicit, to me, I may be thinking about this wrong, but it's to imply. You are implying something. You're trying to guess. It is okay to exceed 1 as a Courant number in some cases, and it can go to 2 or 3 or 5 or 10. Some of the questions that have come up in the chat line are, you know, is it okay to violate this Courant number criterion of 1, and if so, when?
Yes, it is. And the best thing to do is to consult the user's manual for whatever software you're using. And if it's an implicit code, they should give you some guidelines on what some upper limits are on your Courant numbers. And it's going to depend, again, on a lot of things. It's going to depend on what solution schemes being used. whether you're using a complete version of the Saint-Venant equations, conservation of momentum, or some simplification. You can usually get away with a larger Courant number for the simplified version. But yeah, ultimately though, it's up to you to make sure that the results are making sense, number one, and number two, that you can use smaller time steps and you're not going to see a much difference in your results. And so that's the ultimate check, is to see, hey, how does my answer change with some smaller time steps? Am I seeing much of a difference as I decrease my time step? If not, then I'm okay with a Courant number of say 2 or 3 or 4. But I would say as a first cut, it's always a good idea to try, to the extent practical, to keep your Courant numbers around 1 or less, and only back off of that if you absolutely need to buy yourself a little bit of model efficiency.
Thanks. And there are analogous systems all over the place, from people who design excavator buckets to bullets and silencers and guns. All of these things, you know, when you get into fluid dynamics or even into metal fatigue and things like that, you know, the finite mesh and the finite element, finite volume, finite difference, those kinds of things, those concepts don't come up just for flood modelers. So sometimes flood modelers dive into these things and think these things are unique to us, but in a lot of cases, these elements are all over. This time step convergence, for example, I just saw this chart in that example that I showed you for the beer can. You know, as you modify your time step, whether it's a 1D, a 2D, or a 3D model, you should start getting convergence, and where you start seeing that after a while, cutting your time step isn't helping you at all in terms of the accuracy of the results. And so once you start seeing it converge, then you can probably back off a bit and say, okay, I've gone as far as I need to go. Otherwise, I'm just wasting computing time. So with that, let's just go back around. We've got about 10 minutes to go. And what I'll have you do is just, instead of me picking the question and asking you the question, out of those that are, you know, start maybe with those that have been upvoted the most, or with those that you have answered. If you could again just restate for the group here one of the questions that you've addressed or would like to address. We'll just go through and have everybody pick one of your favorites here, because we probably won't be able to get to them all. Let's go back kind of in order. Let's start with Casey, and then we'll go over to Mike.
So yeah, there's a question about the Courant number. Is it necessary for stability? And I think others answered that. It really depends on what model you're utilizing. But if you are utilizing a model that does require a Courant condition to be satisfied, I would say that, you know, if your time steps start getting too small and your model runtime starts to get too large or too expensive for you to run, I would go back and make sure you review that element and that cell size to make sure it's the resolution that you need to, one, accurately resolve your terrain, but also review and see if you actually need that small element cell size for the analysis and design you're performing. So for example, if you're doing a flood inundation model, you likely would not need a high resolution mesh to get water surface elevations. And so you may be able to relax that cell element size. Conversely, if you are doing a more detailed analysis, like for a bridge scour, then yeah, you may need that more resolved cell size. So yeah, if you start getting weird answers, or if your model time starts, if you have a really small time step or very long model run times, definitely go back and review that mesh.
Ah, thanks. Mike, anything that you've picked up on that you'd like to share with the group?
Well, there was a question early on, kind of, Cray, when you're talking about the H&H course, and someone asked about specific model examples, and I think it's kind of been demonstrated here is, you know, there are general topics that will be, you know, specific applications to different regions, and hopefully we can get to most everyone or every region. So because they're, you know, the different, you know, like Australian hydrology and US hydrology are different than, you know, the hydrology from Amsterdam. So, you know, even though the physics are the same, the kind of applications are just a little unique. So
Yeah.
we're going to try to do our best to hit all of them.
Exactly. All right, and just again as a preview, everybody you see here today is going to be helping out with these courses coming up, and so we'll try and get some perspectives from all around the world, not just in any one geographic location. Hubert, you want to go ahead and pick one of the questions that you've of the many that you've been answering here to highlight?
Look, I'm going to maybe to bring something else that has not been mentioned.
Okay.
It's validation.
Yes.
I mean, every time we do some numerical modeling, and it's not just in hydraulic engineering, in any field of engineering, when we do some numerical modeling, we need to validate our work. Now, in some situation, we may have past flood on past flood levels, or possibly sometimes surface velocities at various points on gauging station, which enable us to test our numerical model. But there are also a number of projects where we would not have validation data set or past flood history. And in this case, I think there's an important point of the value of physical or analytical solutions. If we do not have physical data, we may consider to test our numerical model in a situation where there is an analytical solution. I mentioned the dam break wave solution of Bruce Hunt, the monoclinal wave. There are a number of solutions that could be used to test our numerical model, even if it's not a true validation.
Thanks. Chris, any comments that you wanted to highlight?
Yes, there's a question from Thomas. He addressed specifically to me, so I'll take that one. And he brought out a comment from the HEC-RAS manual. And again, I just want to highlight that every software is different. They have different solution schemes, and so it's always a good idea to read what are the conditions or suggestions or guidance for Courant numbers for the modeling software that you're using. And Thomas points out that HEC-RAS suggests a maximum Courant number of 1 and a minimum of 0.1 for a rapidly rising hydrograph. Now, I think that comes out of the 1D section. And that just really speaks to the fact that when you have a rapidly rising hydrograph, you're going to have very high velocities. And so this is guidance, Thomas. It's a suggestion. HEC-RAS, like a lot of other implicit models that are out there, are not strict with Courant number. In other words, you don't have to be below 1, but they found that in certain conditions, it's a good idea to have your Courant numbers around 1 or less, and in this case for a rapidly rising hydrograph. If you dig deeper into the manual for 2D modeling, you'll see that there's some guidance on whether you're using the full shallow water equations or you're using the simplified diffusion wave. And with the diffusion wave, you can get away with Courant numbers a little bit higher, say in the 3 to 5 range even. That doesn't mean the answer is correct. It's still ultimately up to you to verify that the results you're getting make sense, and to Hubert's point, to validate and calibrate your model, if at all possible, with historical data.
Thanks. That's absolutely key, absolutely critical. We're getting toward the end of it here. If we could maybe see the poll results, if you could pop those up. Everybody may see these on a different part of your screen. I'm going to have a look here and just scroll through. But what we asked everybody, and now that we've given these presentations, it might be kind of interesting, is whether you actually consider the Courant number when you're doing your modeling. And it's pretty much split right down the middle. About in terms of people who don't use it at all because they're not modelers, and those who use it never, seldom, often, or always. So I hope now that you've seen a little more of this, even if you're using a model that will pick it itself, sometimes you may want to go in and have a look at whether it's needed, and you may need to optimize your computation time by potentially assigning a fixed time step that might be more appropriate than what the model might pick. You might know more about it than the model does. So in some cases that might be appropriate. And whether the next question then was whether you use the diffusive wave approximation. That's again split about 1/3, 1/3, 1/3 in terms of whether people are using that approximation or not. So with that, I think we may have just some quick closing remarks from everybody. But what I'll say, we used to have used to do live courses, they're coming up back again this year. I think it's been a couple of years now since I've even been on a plane. But I used to like to go around and and do things. And I've got utensils and brownie pans and little things like this to represent the grids and little toys that I've got. I'll take syringes and we'll spray it and look at the velocity of the water and turn kinetic into potential energy and vice versa. We'll take I'll take things and spin it around and does this yo-yo over my head that's going in a constant speed, is it accelerating? And some people will say, no, it's not accelerating because it's going at a constant speed. And then we start thinking about, well, wait a second. No, it is accelerating because the velocity as a vector is changing, even though its magnitude is not. So maybe an acceleration term might be appropriate to consider. And so when you have water going down a channel and it's banking up with some super elevation and there's some inertial terms, you need to make sure if you start using approximations that you know which terms that you have ignored. And so with that, we're going to try and do our best to make this upcoming course series as interactive as possible, as much like it would have been face-to-face as we can walk around and do things and show you analogs. We want to make it as interactive as possible for you. I hope you sense from our instructors here that we're passionate about what we do, and we'd like to pass that what we've learned and what we've gained in the water sector along to you as the attendees. So before we pop up the concluding slides, which will have some upcoming courses and things, let's just have everybody give some closing remarks and say goodbye. Let's go back through in the same order that we did before. Casey, then Mike, then Hubert, then Chris. Over to you, Casey.
Yeah, no, great discussion, great comments, great questions, and looking forward to seeing everyone during the H&H Essentials course.
That's good. Mike?
I echo that. Yeah, and I just remind, it goes back to physics and the data that you have available, and the model has to be appropriate to the question you're trying to answer.
Sounds good. Okay, Hubert, over to you.
I cannot agree more to what has been said. Thank you everyone for attending.
Excellent. Chris, wrap it up for us.
Yeah, thanks everybody. Hope to see you in the class where we'll have a little bit more breathing room to dive into these topics even deeper.
Yeah, we had to pick, we just wanted to pick certain ones for you to highlight. Frood was one of them, and Frood rhymed with dude. Courant rhymed with Saint-Venant, so we picked those. We could have picked any of them, okay, to give you for free. The rest of them will be part of this course series that you can sign up for. It'll be available on demand after it's recorded. And yeah, you'll see some of these links here. Do fill out the survey for us. Let us know what you want to see more of. And then, yeah, have a look at some of the content that's out there. Lots of free webinars coming up still this year. We've got tons of TwoFlow webinars. I saw a bunch of TwoFlow questions on here. Any of the questions that came in on the chat line, we'll try and have our instructors have a look at those and reply to you individually if we can, or we'll post the results. Go back to the YouTube channel and the Australian Water School channel at the end through the website, and you should see links to the resources, which will include any of the questions that we didn't get to. Thanks for all those that came in. We can never possibly get to all of those questions, but I hope we hit the ones that were most relevant to you. So with that, we'll sign off for the day. Thanks so much for attending the webinar today. We hope to see you again soon with the Australian Water School. Bye-bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.